Okay, so we have one of these radioactive isotopes here, californium. It uses the same function as in the previous problem. The future amount, or in this case, the amount remaining at any time t, is equal to the initial amount times e to the kt. We've been given an initial amount of 200 milligrams. And we know that the half-life is 333 days, so that will go in place of t right here. So in order to solve for the growth rate, or in this case the rate of decay, we're going to have to allow t to equal 333 days, and then our 200 milligram sample after 333 days will be reduced to 100 milligrams. So 100 milligrams remains if you start with 200 milligrams and allow 333 days to pass. So if you divide by 200, you're going to have 1/2 equals e to the k times 333. If you take a natural log on both sides, natural log cancels the base of e. So now you have the natural log of 1/2 equals k times 333. And then if you divide by 333, you get a value for k that equals natural log of 1/2 divided by 333. So now we go back up here, and the amount remaining at any given time t is equal to 200 times e, the natural log of 1/2 times 333 t. Okay. So for 38, we have some kind of a liquid solution here who's got a hydrogen ion 4.51 times 10 to the negative 6. We have to plug that into the pH formula here to figure out what the pH is. So pH is negative log of 4.51 times 10 to the negative 6. Now this expression inside here, 4.51 times 10 to the negative 6, it's scientific notation, and you might consider this to be one number, but you can really consider it to be two numbers, and then you could use the property of logarithms, the product property, where if you have log of x times y, you separate that into the log of x plus the log of y. We're going to do a similar thing here. We have 4.51 times 10 to the negative 6. So we're going to split up that single logarithm into the sum of two logarithms. And then I'm going to distribute this minus sign, so we have negative log 4.51. And then log cancels the base of 10, so that's just really a negative 6. But then when you distribute a minus sign to a negative 6, it becomes plus 6. And then it says here the log of 4.51 is 0.654, so this is negative 0.654 plus 6. And if we simplify that, we get 5.346. And that's the pH of that solution. Okay. So we had a 5.2 magnitude earthquake, it says, in 1962. We may very soon be experiencing 7.5 magnitude. So the question is how much more intense? That would be the I part right here of the magnitude formula. So in 1962, we have 5.2 equals log of I over S. And then future, hopefully far in the future, we have magnitude 7.5 equals log. Now, this one's going to be more intense, so we're not just going to use I over S. But the question is how much more intense, and that's what we're trying to answer. So I'm going to let this equal X. How much more intense? So it's going to be X times the original intensity over S. This is X times this intensity over here. So 7.5, I'm going to manipulate this expression inside the logarithm. It's going to be the log of X times I over S. And then going to employ the same property as here when you're multiplying two inside of a logarithm. You separate that into the sum of two logarithms. So 7.5 equals log of X plus log of I over S. But now we can make a substitution. Log of I over S equals 5.2. So this is really plus 5.2. And if you subtract 5.2 from both sides, you're going to get 2.3 equals log of X. Now we're solving for X, and remember X is how much more intense this earthquake would be. X is inside of a logarithm. We can't solve for X until we get rid of the logarithm, so since it's a common logarithm, use a base 10 on both sides. So X equals 10 to the 2.3. Now 10 squared is 100, so that would be 100 times more intense. 2.3 is a little bit larger, so this is more than 100 times the intensity. So it's pretty significant. It doesn't seem like a huge jump on the Richter scale, 5.2 to 7.5, but in terms of intensity, that's pretty intense. So now with a calculator, you would want to go further and actually get a more exact answer or a more approximate answer. But we'd have to leave it like that.